excitation. So here's our forcing function. At time is less than 0, we have 0 force, and then suddenly at time 0, we have a sinusoid as our forcing function of amplitude f0 and frequency of omega, which is the omega of my choosing, okay, the frequency of the oscillation. So there's my equation of motion, my differential equation of motion, mx double dot plus kx equals f0 sine omega t, okay, which is that function there. At time is greater than 0. So what I do is again, it's going to be the addition of xpi plus xcf, xcf being the undamped free oscillation equation, okay, which is there. And then we try our trial solution, which is a sinusoid. Whenever you've got a sinusoid, you've got this as your trial function. A mix of cosine and sine at that frequency omega, which I'm giving the system, okay? So that's the frequency, it's fixed. Okay, if I apply something of 5t, then omega here will be 5 in my trial function. What I've got to find is alpha and beta. And the other condition here is where omega doesn't equal omega naught. Okay, because in that case, when omega equals omega naught, your trial function is actually slightly different. Okay, and in the notes I go through that special case, but it's not in the presentation because it's not, it's not vital for you to know. But if you look at page 46, you can see that it's basically this function multiplied by t, and that's what you've got to do when you have omega equaling omega naught. But we're not dealing with that. Omega doesn't equal omega naught in this case, and so that is my trial function. And if I take the derivative of that trial function with respect to time twice, what happens is you end up with the same thing multiplied by a minus omega squared. Okay, because you take the derivative of this, you get minus sine, and omega coming out. Here you get cosine. Take the derivative again, that minus sine turns into minus cosine. Okay, minus cosine, and then obviously your what was the cosine with the first derivative comes out to be goes back to being sine. So finding the second derivative, you end up getting that, and then obviously you can substitute it into your equation of motion. So when we had x double dot, we've got minus, and then obviously this term, plus k times by x equals f naught sine omega t. Okay? And what you can do is you can see quite clearly that this term and this term are the same. So you take that out, and then you divide by what's left. So we have a k minus m omega naught squared, m omega squared. So that drops down here, and you end up with alpha cosine omega t plus beta cosine, beta sine omega t equaling the forcing function times by sine omega t divided by this k minus m omega squared. And what you do to solve for this equation, what's alpha and beta? Well, basically, you group the sine terms together and the cosine terms together. Okay, so obviously this applies, because you've got a sine omega t and a sine omega t. It's quite clear to see what beta is, yeah? Sine omega t drops out, sine omega t drops out, and you end up with this term. Alpha cosine omega t, well, there's no cosine term over here. So this lot must be 0. The only way for this to be 0 is for alpha to be 0. So it's quite clear that beta is f naught divided by k minus m omega squared, and alpha is 0. So the general solution gives us this, okay? So remember our xpi was alpha sine omega t plus beta cosine beta sine omega t. So obviously beta had a term and alpha has 0. So that's our xpi. There's our general solution. We then apply initial rest conditions. So we take the first derivative. Okay. So all the terms are remaining because they're sinusoids. And we solve for initial rest conditions. Okay. So when time is 0, x is 0, displacement is 0, so that's a1. That stays here. That's 0, and that's 0. So a1 must be therefore 0. Okay. With the first derivative, this term drops to 0. That's disappearing. We've got a2 omega naught times by, and that's 1. Okay. And then we have f naught omega k minus m omega squared times by 1. And so it's quite clear that we can work out what an a2 is. a1 was 0, a2 is minus omega upon omega naught f naught divided by k m omega squared. And so you can plug it in and you end up with this as your initial rest conditions. So you have a sinusoid, depending on your value of omega here and your omega naught here, you've got two sinusoids basically equal, added together. They're subtracted here, but it doesn't really matter. Okay, so depending on your frequency, you're going to end up with a single sinusoid, or a mix of sinusoids. Okay, they're going to be on top of each other. One might be a small ripple, the other one might be a big one. It depends on your values of omega and omega naught. And like I said, this is only valid for when omega doesn't equal omega naught. Okay, if that is the case, then you have to use the special case that's in your notes. Okay, the two frequencies were equivalent. It's clear to see that x would tend to infinity. Okay, which obviously doesn't make sense because you'd end up with 0 down here. If omega equals omega naught, you'd end up with 0 down here, because we know that omega naught is root k upon m. Okay, well, if you stick in that in here, you end up with this becoming 0. What about if you offset it? So you have a function that looks like this. So at time equals 0, we've got 0 force, and then suddenly you offset it by a certain forcing function, and then you also have a sinusoid, which is a possibility. Well, what you do is you end up with mixing the two equations. Well, here you've got, basically you've got a constant forcing function and a sinusoid. And so you take the solution for the constant forcing function, that's part of it, you then add on the solution for the sinusoid. And so there's our bit for the constant forcing function, and there's our bit for the sinusoid. Okay, so you just add them together and you get your solution.